This is Unit 3, Atomic Structure in the Periodic Table. Dalton and the Atomic Theory. What is a theory? So essentially, a theory is a guess. In science, we use the theory to describe a guess about a natural phenomenon. However, a scientific theory has substantial evidence to support that theory. Before Dalton, there were many different ideas about atoms in different parts of the world. Around 600 BCE in India, a philosopher considered all matter was made of 4 types of atoms: earth, fire, air, and water. In Greece, Democritus was the founder of atomism in the ancient era. He believed that there were 2 elements, atoms, and the voids in which atoms moved. Everything was created by the relocations of indivisible atoms. John Dalton was born in Cumberland, England in 1766. He began teaching at just 12 years old. Dalton was particularly interested in weather and even kept a daily weather journal. He was later called the father of meteorology. His most influential work is the atomic theory. He died of a stroke in 1844. So how did he come up with the atomic theory? It's difficult to say. Even Dalton himself couldn't say completely, but he said it was based on his theories of partial pressure. Dalton's model of the atom was a sphere. When Dalton proposed his model, he didn't know about protons, neutrons, or electrons. His model was a very small sphere, like a marble. So what did Dalton's atomic theory say? All matter is composed of extremely small particles, called atoms. That's still true. Atoms are indivisible and indestructible. What we know now is that atoms are made of protons, neutrons, and electrons and can be split in nuclear reactions. Different atoms combine in simple whole number ratios to form compounds. That's still true. Atoms of a given element are identical in size, mass, and chemical properties. Atoms of a given element are identical in size and chemical properties, but not mass. We have isotopes. Those are atoms of the same element that have a different mass. Atoms of a specific element are different from those of another element. That's still true. And in chemical reactions, atoms are separated, combined, or rearranged. And that is still true. The history of the atom. So after Dalton, there was J.J. Thomson. John Joseph Thomson was born in Cheetham Hill, England, on December 18, 1856. He was admitted to college at only 14 years old. He published 13 books, including The Structure of Light, The Corpuscular Theory of Matter, Rays of Positive Electricity, and The Electron in Chemistry, and more than 200 papers. He was knighted in 1918 and became the Master of Trinity College until his death in 1940. Thomson found that cathode rays contained negatively charged particles. They also contain particles which are thousands of times lighter than atoms. Thomson used the cathode ray tube to show the existence of electrons, which are very small negatively charged particles. He created the plum pudding model of the atom, which shows that the atom is a uniformly positively charged sphere containing electrons. Ernest Rutherford was born in New Zealand on August 30th, 1871. He was the 4th child of 12. His mother was a school teacher. He started college at 16. In 1894, he won a scholarship that allowed him to go to Trinity College in Cambridge. There, he was a pupil of J.J. Thomson. He died in 1937 and was buried in Westminster Abbey near Sir Isaac Newton and Lord Kelvin. Rutherford found that almost all of the mass of an atom is contained in a positive, dense center of the nucleus. Rutherford used the gold foil experiment to find the existence of the nucleus. Rutherford studied how positively charged alpha particles interacted with solid matter. By aiming the alpha particles at a thin sheet of gold foil, Rutherford expected the alpha particles would pass completely through the gold foil. However, the majority of the particles went straight through. Only a small percentage were deflected back. Niels Bohr was born in Copenhagen on October 7, 1885. His father was a professor at Copenhagen University. During World War II, he went to America and was part of the Atomic Energy Project, the group that developed the atomic bomb. After the war, he became an advocate for peaceful nuclear power. He died in Copenhagen on November 18, 1962. Bohr proved that electrons travel in specific areas around the nucleus, called shells. Each shell can only hold a certain number of electrons. He also created the Bohr model. Inside of the nucleus are protons and neutrons, and each of the shells that are around them hold certain numbers of electrons. The first shell can hold 2, the second shell can hold 8, the third shell holds 18, and the fourth shell holds 32. So when filling the shells with the electrons, you always start at the smallest shell and then add electrons to the outer shells as you need them. Robert Millikan was born in Morrison, Illinois on March 22, 1868. He loved tennis and golf. During World War I, he helped develop an anti-submarine and meteorological devices. He won the Nobel Prize for Physics in 1923. He died in California in 1953 and held honorary doctorates from 25 universities. Millikan used the oil drop experiment to find the charge on an electron. A chamber is filled with 2 metal plates. The plates have a positive or negative charge when an electrical current is added. A mist of oil droplets are sprayed into the top of the chamber. Some of the oil droplets get a negative charge as they fall through the holes in the metal plate. By using the voltage that is applied, the charge of the droplet can be calculated. This experiment led to the determination of the charge on an electron. Erwin Schrödinger was born in Vienna, Austria, on August 12, 1877. He was an only child. He escaped to Italy after he angered Nazi officials for his open opposition to the party. He is best known for Schrödinger's cat. He died in 1961 in Vienna. There is a crater on the moon named after him. Schrödinger used mathematics in his wave equation to determine the probable location of an electron. His explanation of electron location was different from Bohr, since Bohr said electrons were in distinct pathways. Schrödinger's cat was a thought experiment. Imagine a cat, a radioactive material, a Geiger counter, and a vial of poison are inside of a box. If the radioactive material decomposes, then the Geiger counter detects it, then the hammer strikes the vial and the poison kills the cat. This experiment was proposed to disprove the Copenhagen interpretation, which said that a quantum particle can exist in all probable states at once. So the first model of the atom was Dalton's in the early 1800s, and he said that atoms look like solid spheres. Thomson had the plum pudding model. There was a large positive charge dotted with negatively charged particles. Then Rutherford, in the early 1900s, came up with the nuclear atom, the dense positive nucleus surrounded by electrons. Bohr said that there was a dense positive nucleus with electrons arranged in orbitals. And in the mid-1900s, Schrödinger came up with the electron cloud model, which said electrons are not in exact pathways, but have areas of high probability. Atomic structure. What is an atom? An atom is the smallest particle of an element that retains the properties of the element. Atoms are made from 3 subatomic particles: protons, neutrons, and electrons. Protons and neutrons are in the nucleus. Electrons are in the cloud around the atom. The atom is mostly empty space. So the symbol for a proton is a P with the superscript of a plus sign. Protons have a positive charge, and they're found in the nucleus. and the mass is 1 AMU. An AMU is an atomic mass unit. It's used to measure the mass of subatomic particles. A neutron has an N with a superscript 0. It's neutral for the charge. It's also found in the nucleus and also has a mass of 1 AMU. Electrons are an E with a negative. They have a negative charge, and they're found in the cloud. They have a mass of 0.0005 AMU. The atomic number is also the number of protons and electrons in neutral atoms. The mass number is the number of protons and neutrons. To find the number of neutrons in an atom, subtract the atomic number from the atomic mass. So atomic mass minus protons gives you the number of neutrons. Remember, the atomic number is the number of protons. It is also the number of electrons only if the atom is neutral. So to find the atomic mass, you add protons and neutrons together. So looking at these, this is what an element would look like on the periodic table. Here's the atomic number. Here's the mass number. This is the symbol. So protons are equal to the atomic number. Electrons are also equal to the atomic number. And to find neutrons, we take the mass minus the number of protons, so we would have 10. Over here we have 29 for our atomic number, so that's the number of protons. 29 would also be the number of electrons, and we'll call this 63 minus 29, so we have 34 neutrons. So quick check. An atom contains 35 electrons, 27 protons, 19 neutrons. What is the atom? So if we look at the number of protons, this tells us what the atom is. So 27 protons would be cobalt, and our mass is the number of protons plus neutrons. So use your periodic table to complete the chart. So the first element is manganese. Manganese symbol is Mn. Has a mass of 54. It has 25 protons. That's the atomic number. The electrons would be equal, and our neutrons would be 54 minus 25, so 29 neutrons. Lithium, its symbol is Li, has a mass of 7, has 3 protons and 3 electrons, and neutrons, 7 minus 3, so it has 4. So complete the rest of the chart on your own. The mass of radium is 224. The mass of nitrogen is 14. And the mass of mercury, 220. Ions and isotopes. So what's so important about ions and isotopes? Ions are very important in chemical reactions and play a very important part in biological systems. Some isotopes are unstable. They are radioactive and will decompose. Sometimes this is good, nuclear medicine and nuclear energy, but sometimes it can be bad, nuclear meltdowns and radiation poisoning. What is an ion? An ion is an atom that has lost or gained electrons. Cations are atoms that have lost electrons and have a positive charge. Anions are atoms that have gained electrons and have a negative charge. Make sure you color in the periodic table with cations and anions. So how would an atom become an ion with a +3 charge? To become positive, it would have to lose electrons. So this atom would lose 3 electrons. What are isotopes? Isotopes are atoms of the same element that have different mass numbers. they have more or less neutrons. Let's look at carbon. There are 15 isotopes of carbon. The three most common are carbon-12, carbon-13, and carbon-14. How many neutrons are in each isotope? So the number after the hyphen is the mass number. So carbon-12 has a mass of 12, also has 6 protons. So 12 minus 6, it has 6 neutrons. Carbon-13 has a mass of 13, so 13 minus 6, it has 7 neutrons. And carbon-14, we would have 14 minus 6, because our proton number doesn't change, gives us 8 neutrons. So there are 3 different types of notation, or ways of writing different elements. The first is hyphen notation. So to write an element in hyphen notation, you write the element's name, a hyphen, then the mass number. So like the example before, carbon hyphen 12. In abbreviated hyphen notation, you write the element's symbol, a hyphen, and then the mass number. So C-12. In AZX notation, you write the element symbol, so carbon. The atomic number goes to the bottom left, and the mass number goes to the top left. If there's a charge, it would go to the right. So write each of these in each of the different types of notation. So uranium, in hyphen notation, the symbol is U-238. To write this in AZX, uranium 238 is the mass, it goes at the top, and 90, which is the atomic number, goes at the bottom. Use your periodic table to write the rest of the notation. So using your periodic table, we're going to complete the chart. So this element has 53 protons. That would be iodine. The atomic symbol is I. We need the atomic number, it goes on the bottom, 53, and the mass number goes at the top. That would be 53 plus 74, so 127. Our atomic number is the same as the number of protons, 53, and the mass number, which we just found, was 127. Next we have nitrogen. It tells us our atomic number, which is 7. Our mass number is 14. We know that we have 7 protons. Our neutrons we find by subtracting the number of protons from our mass number. So this time that's 7. And our electrons, we have a -3 charge. So to get a -3 charge, that means we had to gain electrons. We started out with 7 and we gained 3. So now we have 10 electrons. The next one is sulfur. So we know the atomic number is 16. So we have 16 protons. Our neutrons are our mass number minus our protons. So that's 20. The symbol for sulfur is an S. We know the atomic number is 16. The mass number is 36. And now if we have a charge. So we have 16 protons and 18 electrons. So this would give us a charge of 2 minus. The last one is radon. So figure out what the AZX notation, atomic mass, and atomic number are for radon. Average atomic mass. How do we calculate the mass of the atom? Remember that we add protons and neutrons together. If we do that, our answer should be a whole number. Now, look at the mass on the periodic table. The mass numbers on the periodic table are not whole numbers. So, how did they come up with those values? they used weighted averages of the known isotopes. Remember, an isotope is an atom of the same element that has a different number of neutrons, or a different atomic mass. What is a weighted average? A weighted average is the average that is calculated by using the percentage of each component. It is also the way your chemistry average is calculated. Formative grades are 40%, summative grades are 60%. This allows some grades to be more important than others. So if you had an 80 for your formative average and a 90 for your summative, how would you figure your grade? So formative grades are 40%. So we would have 80 times that 40% plus 90 for the summative times 60%, and then we add those together. So your average would be an 86. So calculate the average atomic mass of gallium. If it is 60.1% gallium-69 and 39.9% gallium-71. So to find the average atomic mass, the first step is to convert percentages to decimals by moving them 2 places to the left. So we have 60.1, and we'll make it 0.601. We have 39.9, we'll make it 0.399. Then we multiply the mass by the corresponding decimal. So gallium-69 times 0.601 and gallium-71 times 0.399. Then we add those together. So our average atomic mass is 69.798. Calculate the average atomic mass of bromine. The 2 isotopes of bromine have atomic masses and relative abundances of 78.92 AMU at 50.69% and 80.92 AMU at 49.31%. So the first step is we're going to convert our percentages to decimals, then multiply, then we add them together. So our answer is 79.91 AMU. Light in the electromagnetic spectrum. Electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. It behaves as both a wave and a particle, called a photon. This is known as wave-particle duality. Electromagnetic radiation does not have mass. Examples of electromagnetic radiation are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Let's look at a wave. The wavelength is the distance from the crest of one wave to the same point on the crest of the next wave. So, wavelength. The amplitude is the distance from the midpoint to the crest or trough, and the frequency is the number of waves that pass through a certain point in a given amount of time. All electromagnetic waves travel at a constant speed in a vacuum, 3.00 times 10 to the 8th meters per second. We can determine the frequency or wavelength of a wave by using the formula C equals lambda nu. The wavelength, lambda, is measured in meters. The frequency, nu, has the units hertz, or waves per second. And the speed of light is a constant, c equals 3.0 times 10 to the 8th meters per second. The normal position of an electron within an atom's electron cloud is known as the ground state. When a photon with sufficient energy hits an electron, the electron becomes excited and jumps to a higher shell. These excited electrons must fall back to the ground state by emitting the excess energy as a photon of light. Think about fireworks. We can also calculate energy using the formula E equals hf. E is the energy of light in joules, h is Planck's constant, and F is the frequency in hertz. The frequency of a photon determines the energy of a photon. So how can an electron become excited? By heating, by being struck by a photon, or by being hit by another electron. The photoelectric effect. Electrons can be ejected from the surface of a metal when a light shines on it. These electrons are called photoelectrons. A German physicist named Heinrich Hertz was the first person to observe the photoelectric effect in 1887. Thomson later identified the sparks Hertz noticed as electrons. We can compare wavelength frequency and energy. If we have a long wavelength, we would have a very low frequency and low energy. So draw a wave, has a long wavelength. If we have a very short wavelength, we have a high frequency, high energy. So a drawing of this wave, wavelength and frequency are indirectly proportional. So if wavelength goes up, frequency would go down. Wavelength and energy are also indirectly proportional. But frequency and energy are directly proportional. If you increase the frequency, you increase the energy. The hydrogen line emission spectrum. How does it work? When an electrical current is passed through a sample of hydrogen gas, the gas will produce certain colors of light. When that light is passed through a prism, the light is split and you can see 5 distinct lines. This is called the emission spectrum of hydrogen. Different elements have different emission spectrums. What's it used for? Since each element has its own unique line emission spectrum, this is used to determine what stars and the atmosphere of planets are made of. The periodic table. How was the periodic table created? Dmitry Ivanovich Mendeleev was a Russian chemist. He noticed that when elements were ordered by increasing atomic mass, there was a periodic pattern in their properties. He accurately predicted the existence and properties of previously unknown elements. Henry Moseley was a British chemist that demonstrated that when the properties of the elements were caused by their atomic number, he arranged the elements by atomic number instead of mass. This solved the problems in Mendeleev's table and is what became the modern periodic table. The layout of the periodic table allows us to make predictions about elements. The columns that run up and down are called groups. The rows are called periods. The atomic number is also the number of protons and electrons in a neutral atom. The mass number is the number of protons and neutrons added together. To find the number of neutrons in an atom, subtract the atomic number from the atomic mass. So atomic mass minus protons equals neutrons. The periodic table can also be divided up into metals and nonmetals. So this line, the stair-step line, everything that is touching the stair-step line are metalloids. Everything to the right of that line are nonmetals, and to the left of the line are metals. So metals are shiny, they're good conductors of heat and electricity, they have high melting points, they're malleable and ductile, and most of them are solids at room temperature. Nonmetals are dull, they're poor conductors, they have usually low melting points, they're brittle, and they could be solids, liquids, or gases at room temperature. So metals and nonmetals have different properties. Metalloids share properties with both metals and nonmetals. The periodic table. Families. The families on the periodic table have the same properties. This means you can tell a lot about an element depending on the group that it's in. The first group are alkali metals. These are all group 1 metals. They're very soft, they're shiny, they have a high thermal and electrical conductivity, they have a low density, and they will all react with water. These metals are going to lose 1 electron and have a positive charge. Some of the uses are batteries, fireworks, medicine, and lamps. Group 2 metals are the alkaline earth metals. They are harder than Group 1 metals. They're also shiny. They have a high thermal and electrical conductivity. They're more dense than Group 1. They react with water as you move down the periodic table. They will lose 2 electrons and have a +2 charge. Some of the uses include antacids, laxatives, plasters, cement, drywall, and X-rays. The next group is the transition metals. These are groups 3 through 13. They are very hard metals. They're shiny. They have a high thermal and electrical conductivity, a very high density, and very high melting points. Some of the atoms have multiple oxidation states. Some of the uses are replacement joints, construction, and jewelry, like gold and silver. Next is group 17. These are the halogens. Fluorine and chlorine are gases at room temperature. Bromine is a liquid, and iodine and astatine are solids. They are highly reactive nonmetals. They are toxic and potentially lethal. They have high electron affinities, meaning they will take electrons from other atoms. Some of the uses are disinfectants, salts, lamps, and refrigerants. Group 18 is the noble gases. These are all inert gases. They have 8 valence electrons. They are monatomic gases at room temperature. They have very low melting and boiling points. Some of the uses are shield welding arcs, lighting, and scuba diving. The next is a series. The lanthanide series starts with lanthanum. These have a very silvery shine. They tarnish very quickly. Some of the uses are ceramics to produce a glass-like covering and superconductors and lasers. The next series is the actinide series. These are all radioactive. Most of them are man-made. They are all unstable. They have a silvery or silvery white shine. Many ignite at room temperature. Some of the uses are nuclear fuel, powering pacemakers and smoke detectors, decorative lights, and they powered the Apollo 12 lunar mission. The periodic table trends. What are periodic trends? Periodic trends come from the arrangement of the periodic table. They allow chemists to easily predict an element's properties. Trends exist because of the similar structure of the elements in different families. Electronegativity. Electronegativity is an atom's ability to take electrons. It increases as you move up and to the right on the periodic table. The Pauling scale is most commonly used to quantify electronegativity. Ionization energy. This is the amount of energy that is needed to remove an electron from an atom. It increases like electronegativity as you travel up and right across the periodic table. Atomic radius. This is the size of the atom. It increases as you move down and to the left of the periodic table. Electron affinity. This is the change in energy of a neutral atom when an electron is added, or the likelihood of gaining an electron. It increases as you move up and to the right across the periodic table. Melting point. Melting point is the energy required to change a solid into a liquid. Generally, metals have a higher melting point. Nonmetals have a lower melting point. However, carbon, a nonmetal, has the highest melting point of all elements. Metallic characteristics. Metallic characteristics increase as you move down a group and decrease as you move right across a row. Ionic radius. Because atoms can lose or gain different numbers of electrons, you must look at this trend for each atom. Atoms that have lost electrons, becoming cations, have a smaller ionic radius.
Atoms that have gained electrons, becoming anions, have a larger ionic radius.